So here we see question number 6, and it says that find the EMF developed in randomly shaped wire having ends x and y, where xy is equal to d units and wire is moving with velocity v along the horizontal direction, and xy subtends an angle a with the horizontal. Now they asked to refer to the figure given below. Basically इस question में हम लोगों को एक randomly shaped wire दिए जिसके ends हैं x और y, और xy का magnitude हमें दे दिया है उसकी length का magnitude d centimeter d units basically, and the wire हमें दे दिया it is moving with the velocity along the horizontal direction. एंड जो एक्सा है वी आर गिवन वन मोर थिंग दैट वो हॉरिजॉन्टल पे एंगल ए सबटेंड करता है, एंगल थीटा और एंगल ए खुद से विल कंसिडर एंगल थीटा. सो हम लोग को ईएमएफ निकालना है. सो क्वेश्चन देख के पता चल रहा है दैट वील बी यूजिंग मोशनल ईएमएफ इन इट बिकॉज ऑब्वियसली इट इज द वायर इज मूविंग. देयर इज नो कंसेप्ट ऑफ देयर इज नो पॉइंट ऑफ यूजिंग द फ्लक्स मेथड. लेट्स सी हाउ टू सॉल्व द क्वेश्चन.
See, in this question I have given you a randomly shaped wire, right? So you must by now you must get an idea that whatever might be the shape of the wire, you might get the same answer. See, I only gave you the terms like the distance of length of the xy and the angle it subtends with the horizontal. So now I am going to explain how to solve this question. I am going to consider a small part of a wire. Let me think this is the randomly shaped wire. A small part of the wire of length, maybe let me say dx. Okay, I'll probably use the vector method to solve this part. Okay, and because this is moving with velocity v, right?
Right.
And check here. Okay, and its length is dx and is placed in magnetic field B.
That's right.
So because of a small part dx, let me first calculate the EMF developed. So the EMF developed because of a small part dx would be V cross B dot dx.
That's right.
Obviously V is perpendicular to B because B is into the plane of the paper and V is along horizontal, and V cross B will be along this direction.
Exactly.
So if you cross this and this by using right hand thumb rule, you will get this. So it's nothing but we are so V cross B is not parallel to dx.
Okay.
Right? So I am going to leave it aside. The dot product, let it stay like that. It's a vector form.
Right.
So I can write it as d as v b dot dx.
That's correct.
Now I am going to integrate this all over the length of the wire. I have given you the ends as x and y and the length of xy as d units, right?
Right.
When I am going to integrate this, it will be as v b dot dx. This vb is a vector in the pointing upwards.
That's correct.
And dx is varying completely. So this v and b are constants. So I am going to take this out of the integral. But the dot product remains the same. So I am going to integrate from x to y.
Okay.
This dx vector.
Okay.
If I am going to integrate this x to y, I am going to add the small vectors here, over here. If I am going to add the small vectors and integrate this, I will finally get an xy vector.
Right.
You really know now. By adding the small vectors, for example, in this curve, if this point is A, this point is B and this point is C, AB vector plus BC vector is AC vector.
By the simple rules of vector addition.
In a similar way, by the vector addition, if we integrate it over the entire length, we will get as xy. We will get the whole length as xy vector.
That's right.
And this xy vector is making an angle theta with the horizontal, right? So it makes an angle pi by 2 minus theta with v dot b vb vector. So if we the total EMF would be v dot b dot xy, and then if we solve the dot product, it will become vb into mod xy into
Correct.
cos of pi by 2 minus theta,
That's right.
because the angle between the vb vector and the xy vector is pi by 2 minus theta.
And here we have assumed A to be theta.
And now I have mentioned that xy mod xy is d, because the length of the wire is not the length of the wire, the distance between the ends is d. Whatever might be the length of the wire, the ends are at a distance d. This would be the answer. We would finally get vbd sin theta.
That's right. So basically, we saw that this was a long and a little tedious question. But okay, it's important to do such questions for practice as well, because they just make your concepts clearer and stronger. And okay, so this was another typical question on the concept of motional EMF. So this was it for question number 6. Okay, we come to question number 7, and that says that we have to calculate the EMF developed within the disk that is given below in the figure. We can see एक half disk है हमारे पास, और उसका angular velocity हमें ओमेगा दी हुई है, and we have also been given कि उसकी जो magnetic field है B, that points into the plane of the paper, and वो जो half disk है उसका radius R given है. हमें इस disk का EMF निकालना है. This is a very important conceptual question, and it will actually generate some new formulas now. We'll just have a look at it now. Okay, start.
Here initially the disk is placed in a region where there is no magnetic field at all. It is moving with velocity or angular velocity omega, and it is some part of the disk is going to go into the magnetic field slowly. See, initially at t equal to 0, there is no part of the disk inside the magnetic field. So let me think, at a time t equal to t naught, the angle covered by the disk would be omega into t. So at the instant at t equal to t naught, the angle would be omega t naught, right?
That's right.
So only this part of the disk will be inside the region where there is magnetic field. So at this particular time, the flux linked with the disk would be B into the area of this sector, right?
That's right.
There is nothing but omega t by 2 into r square. This is the area of this particular sector.
Right.
So at any time t, the flux would be this much, but the flux would be this much only till the time where the half disk is going to completely insert into the region where there is the magnetic field. Because at time, let me consider at time where the disk is going to completely come into this field. At this time, the flux linked would be B into pi by 2 r square, and this would be the maximum flux. And afterwards, the disk keeps on rotating. Later, what happens is, when the disk rotates, the flux would be gradually decreasing, because the area inside the region where there is magnetic field is continuously decreasing.
Exactly. It's quite logical, in fact, to see that.
So at the time so let me guess. Here this angle is pi. So at the time when omega t equal to pi, that is nothing but at time t equal to pi by omega, the flux in the disk would be maximum. after time t equal to pi by omega, the flux would be decreasing.
Right.
So I am going to write a basic equation here. The phi of t would be b into omega t r square by 2 for time t less than pi by omega.
That's right.
Now for the time t greater than pi by omega, it will be b into pi by 2 square minus b omega t r square by 2, because it's going to decrease from now at the same rate.
Basically, we are finding phi of t for various intervals of time. Okay, like for less than pi by omega and greater than pi. We are considering different intervals.
So the flux is a function of time. So it's changing with respect to time. So there will be EMF induced.
That's
because
right.
EMF induced is nothing but minus d phi by dt. We
Right.
all know this, right? So initially what is happening is the area is going to increase in the magnetic field. That is nothing but the flux linked with the magnetic field into the plane of vapor, that is anti-clockwise direction, is going to increase. So the EMF is going to induce in the clockwise direction.
That's true.
Later on, when the area is decreasing, the flux is decreasing in the anti-clockwise direction. So the EMF this time increases in anti-clockwise direction.
True. Basically, a cycle we see that will follow.
Yes. Okay. Let me plot the graph. No, first let me find the EMF induced. The EMF induced during the time 0 to pi by omega would be differentiation of this b omega r square by 2.
That's right.
But for the time pi by omega 2 pi by omega would be minus b omega r square by 2.
Right. So basically, it gets reversed after a time interval.
Because initially the area is increasing for half time period and later the area is going on decreasing.
That's right.
So if you plot a graph, and after this one complete rotation, this cycle is going to continue. That is nothing but from the time 2 pi by omega to 3 pi by omega. Also, this equation is, the EMF induced will be b omega r square by 2. So we can generalize this as 2n pi by omega to 2n plus 1 pi by omega.
Right.
And
this is
one,
important to see here, that it's important to generalize the result rather than talking in particular terms.
Because the cycle is going to take place continuously.
Exactly. It's not just for one time. So you need to take care of this thing, that otherwise whenever asked particular solution, that is a separate case. In other cases, you always need to mention the general result.
They may even ask the general solution of this in IIT JEE exam paper.
Exactly.
So if we plot a graph, it would be like this. Sorry, I don't have space over here. Okay, I'm going to manage this. Initially, from 0 to pi by omega, it will be positive, right?
That's right.
And later,
It becomes negative for the interval till 2 pi by omega.
later the graph would look like this.
It seems to be a periodic function, exactly.
With a period 2 pi by omega.
Exactly. So basically in this question,
Again, you can even plot a function for flux, by seeing the above relation. Initially the flux would be maximum, right? Initially flux would be 0.
that's right.
there's nothing but initially it would be increasing and later decreasing, increasing, and so on from 0 to pi by omega. At pi by omega the flux is maximum, and 2 pi by omega it's minimum in this direction. They may even ask the graphs of this in IIT question.
That's right. Basically, we saw in this question that how this EMI thing, the flux thing, generated basically a cycle, a period for the motion of this half disk, and basically it will carry on this motion till infinity. We can see that its motion would be the EMF generated would be different for the time interval 0 to pi by omega, then exactly the same magnitude but the sign being opposite for the time period from pi by omega to 2 pi by omega. Basically the sign denotes that the direction has changed. So it will go on doing this. After 2 pi by omega it will again change its direction, and so on will keep on happening. So it was a good conceptual question, although a little lengthy, and just a good practice of electromagnetic induction it just offers to you. So you need to do this very carefully, as these formulas are sometimes used as direct results in the paper. So if you do this 1 or 2 times, you will actually be able to almost memorize the result. So this was question number 7. Proceeding on to question number 8, the question is, consider conducting rail which is movable on a platform very long and is falling under gravity, but magnetic field is present perpendicular to the platform, that is in a horizontal direction. Now rail has a resistance of capital R attached to it which completes the circuit. We have to analyze the motion of the rail. It is basically a subjective question, and इसमें हमें दिया हुआ है कि conducting rail है, ठीक है, उसमें एक प्लेटफॉर्म पे वो मूव कर सकती है, एक बहुत लंबे प्लेटफॉर्म पे, ठीक है, लेकिन जो मैग्नेटिक फील्ड है वो परपेंडिकुलर है प्लेटफॉर्म, इट इज परपेंडिकुलर टू द प्लेटफॉर्म, दैट इज एक हॉरिजॉन्टल डायरेक्शन में, परपेंडिकुलर प्लेटफॉर्म हमारा वर्टिकल डायरेक्शन में. तो हम कह रहे हैं कि वो जो रेल है उसकी रेजिस्टेंस है आर, तो उस वजह से सर्किट हमारा कंप्लीट हो रहा है, एंड वी आर सपोज टू एनालाइज द मोशन ऑफ द रेल स्टार्टिंग फ्रॉम टाइम इक्वल टू t इक्वल टू 0. सो हाउ विल वी डू दिस क्वेश्चन?
See, if there is no magnetic field, let us analyze the motion of this rail. What happens? It falls with directly. It is nothing but a freely falling body. But because of this magnetic field, what happens is this rail completes a circuit, and because of this an EMF is developed, and because of the EMF, a current is produced in it, and because of the current there is a magnetic force acting on the rail in the opposite direction, and because of which this is going to move slowly. I am going to write a differential equation. Based on that we are going to solve the question. If you see the rail, what happens is when this is going to move at any time, if the rail has a velocity v, what happens is there will be an EMF of BLV induced in the circuit, right? And because of this BLV EMF induced in the circuit, the current in the circuit will be BLV by R, and the current in the circuit will be tending will oppose the increase in the flux, right? And because of this current which is flowing in the circuit in this direction, there will be some magnetic force acting on the rail.
We see that visualization is really important in this chapter of exactly what is happening.
See, the current is in this direction and the B is inside the paper. So the force acting on the, we all of us know how to calculate the magnetic force on any moving particle, and because of this current carrying wire, the magnetic force on the current carrying wire would be BIL.
That's right. The
and
formula for force.
In upward direction.
Right.
So the total force acting on the rail would be mg in downward direction and BIL in upward direction. So the effective acceleration of the rail in downward direction would be, if you think it as A, it would be like this, m into dv by dt. and this is the differential equation. And here we know I is nothing but BLV by R. On substituting that, we'll get B square L square V by R and dV by dt.
That's right.
Here the mg, bl, r are constants. It's nothing but a differential equation of v with respect to t.
Exactly.
If we are going to solve this equation, it's actually a tedious process. You can do it by differentiation with a single variable. We all have dealt it in the differential equation chapter in maths. It takes a lot of time to do here, and because of lack of space I am directly writing the result. Maybe it will be like this, it will look like this. If you arrange it,
Yeah, basically just doing simple mathematical calculation and some manipulation, we get our result to be of this form.
no, it's just a manipulation over here. On rearranging the terms, we get like this. At time t equal to 0, the velocity of that is 0.
Right.
So at time t equal to t, let us think the velocity is v, and let us start integrating this. It is similar of a 1 by v form, and if we integrating this and solving it later, we will get v as mg r by b square l square into 1 minus e power minus b square L square T by MR.
That's right.
It's a very important question, and this is frequently asked in IIT JEE. The main theme of the question is we have to identify that the magnetic force is going to act on the rail when it is placed in a magnetic field, because there is going to be current flowing in the rail as it is connected in the circuit, and because of this current which generates a magnetic force on the rail.
That's right. We can easily see that it is a good conceptual question, and it does include a tedious integration over here, but as we said before, your integration needs to be up to the mark, and using that you could have easily calculated the result. It is a little complicated result, but the question basically being another good example of motional EMF. So this was question number 8. Question number 9. A conducting rod of length B is being moved parallel to a current carrying wire placed at a distance A from the rod. We are supposed to calculate the EMF induced. Basically हम लोगों को एक rod दी गई है जिसकी length है B और वो V velocity से आगे जा रही है, and it is moving such that एक करंट कैरिंग वायर एक नीचे एक हॉरिजॉन्टल लेवल पे ए डिस्टेंस पे वो उसके पैरेलल ही मूव कर रही है, एंड हम लोगों को इस रॉड में उस वायर की वजह से जो ईएमएफ इंड्यूस होगा हमें वो निकालना है. सो लेट्स सी हाउ वी गोना वर्क दिस आउट.
Because of this wire, there is going to be magnetic field induced, right? And this will be into the will have the direction into the plane of the paper.
That's right.
And this would be as a function of x, from the x distance from the wire. So if you find a point, if you locate a point at a distance x from the wire, the magnetic field at this point would be mu naught I by 2 pi x.
Exactly.
We would have known that before earlier. And see, if we take the rod, we are going to solve this problem based on the motional EMF.
That's very intuitive now. Okay, we can just make out from the question, I guess, that when the motional EMF is to be used and when we are to use the flux method.
Yes.
Basically, I think that some practice of around 5 to 6 questions will give you a clear idea when you are to use what and what will reduce your work.
Let me consider a small part of the rod placed at a distance x from the wire. And let me think the small part of the rod have a length of dx.
That's right.
And because of small part dx, let me think the EMF induced be dE. And this dE would be V cross B dot dx.
Fair enough.
And here the B is a function of x. That is mu naught I by 2 pi x. Right?
That's
and
right.
B is perpendicular to B, we all know that.
Obviously.
And it is parallel to dx. V cross B is parallel to dx. Because dx is in vertical direction, V cross B is also in vertical direction. So is nothing but we will get as mu naught I 2 pi x dx v into.
And we'll just take the integral on both sides now.
We are going to take the integral, right?
So basically we see at the end of every question, just after you can visualize the question and once you know what you're going to do, you basically come down to integration and then you have to solve a big tedious integral equation.
See, the lower end of the rod is at a distance a. So we are going to integrate it from a, and the upper end of the rod is at a distance a plus b from
Exactly.
the wire. So we are going to integrate from a to a plus b.
So the limits of integration are also very important, as not only the integral, if the limits are different, so your answer could be overall different, and it's very intuitive generally to start the limits from 0, but it's not necessarily that every time it would be 0. We just need to consider the cases and what exactly is happening.
On solving this equation, we are going to get this result.
Exactly, it is a very important result, and it might be used very often directly also. So you could just solve and go through this question again, as it's a good conceptual question. So this